which will talk about temporal data in databases. I won't steal him much more time, and I pass the microphone to him. Thank you, Anton, and welcome.
Thank you. Okay, so hi everybody. I'll try to do my best to move around in a natural way, but it's gonna be tough. Okay, so the topic of today is how to process and manage temporal data in Postgres. So the agenda is basically at the beginning I will talk a little bit what temporal data is, what we consider temporal data. Then we'll focus on two important aspects of temporal data in Postgres, how we can manage them, how we can use them. And at the end, I will describe a little bit what we are working on at UniBZ in this respect. Okay, so temporal data is something that we can find all over the place. So in most applications, we have to somehow process and manage temporal data. So here I just have a few examples. So we have contracts in the HR department where contracts change over time, contracts have a lifespan and so on. Okay, so this is all considered temporal data. Then we have insurance policies which have a lifetime, again temporal data. In the medical domain, we have patient histories, we have different kind of data which is changing over time. And of course, stock market data. In the industrial sector, we have sensor readings of industrial machine production sequences, etc. So what is temporal data? So temporal data is basically data with a timestamp. Okay? So timestamp can be many things. We'll see later on. We'll see two different ones. Plus, the timestamp indicates when the data is valid. Okay? So basically, two examples, a contract has a lifespan. The lifespan says when the contract was valid. And we have sensor readings, and basically the sensor readings have usually attached a timestamp, and this timestamp says when the sensor reading was performed. Okay, so in general, Postgres provides basic utilities to store a timestamp and store different kind of data with time. So here I just put the basic utilities for date and time, so I guess most of you know them already. So Postgres provides us with a data type, timestamp, date, time, and different kind of, let's say, data types, plus many functions which we can use to modify these data types. So just to give you an example, so we have two kinds of timestamps in Postgres. So this is basically a data type that we can use in the database. And we have it with time zone, without time zone, and associated with, we have a lot of functions. We can add days to it, we can add minutes to it, and so on. Okay? So this is probably what most of the people know about how to somehow create table which has a timestamp. Plus, associated with all these data types, we also have calendar functions, and these help us basically to extract valued information out of the timestamp. Okay, so whoever has worked somehow with in any application with dates and time zones knows that this is quite complex, and this is actually a very valuable function that we have in Postgres. Whenever you have a question, just let me know or interrupt me whenever something is not clear. Okay, so these are just the basic utilities. Okay, this is what we have basically to store something which is related to time. The topic of today does not go to these basic data types, but goes into two directions. So we'll see period temporal data. So basically contracts with a lifespan, manufacturing periods, error states which start at a specific time point and end at a specific time point. And we'll see how to manage time series data in Postgres, which are basically sensor reading, stock market, and so on. Okay. So let's see basically what Postgres and its ecosystem has to offer in respect to these two timestamp data. Okay, so first we'll start with the period data. So this is always data where our data is associated with a start and an end. And since 2012, Postgres basically provides a data type which is called range types. So this is more than a data type itself, this is a family of data types. And here basically is something where we can store a start and an end in one single attribute in a table. Range types can have different forms. We can explicitly say anytime, is the start point included, is the end point included or not. Okay, so we can have different forms, and our range type can have different data types. So we can have a range type of type integer, so basically our start and end is given by an integer, it can be a numeric, it can be a date, and so on. Plus also here, the system provides us with many predicated functions which we can use to extract basically information out of this range type. One additional plus is that Postgres also provides us with 3 types of indices which we can use basically to extract, or we can use to index basically data with timestamps. They're very easy to use, and what they basically do, they avoid a lot of programming mistakes. So just let's start with an example. So let's imagine we want to store basically product prices, so prices of products that are changing over time. So basically what we do, we can create a table called, in this case, product prices. We have an integer which indicates which products we are storing the price of. And here, this is basically the period for which this price is valid. And here we use a date range. So this is basically a start and an end of type date. And here we have basically the price, which in this case I just use value float. Okay, so let's see how this looks like. So this, whenever we basically want to insert data here, we have to specify, of course, the product of which we store the price, the lifespan in this kind of format, start and end, plus the associated price that we basically store for this product. And we can have a special field here. So we see here that end is basically empty. So this indicates that this is basically valid till infinity. Okay? So it doesn't have an end. And this is basically how it looks like. So here we have prices of 2 products, which basically change over time. So this is what we can basically store with these range types. And the table looks like this. So what are common queries that you want to do on such kind of data? So one very common query is, what is the price of product 1 today? So this is something that we need in order to find the actual price of the product. What is the price of product 1 at a specific date in the past? So if you sold a product, you want to know the price that was assigned to this product. Or for which products do we have a price on a specific date? Okay? So for which products we had a price registered? Or what were the product prices for product 1 between 2 specific dates? And now I have a task for you. So basically I simplified here a little bit the table, so now we don't have a range type anymore. What we have is basically a product, we have a start point, an end point, and a value. And what I would like to have is basically the prices of product 1 between these 2 time points. Okay? So I would like to have the prices of product 1, so we can directly exclude the second 2, that we had in our database between October 30, 21 and October 30, 22. Okay? So try to think, if I give you these 2 dates, how you can actually create a query which gives you this right result. Does anyone have an idea, at least how to approach it?
Yes, of course.
Okay.
But you have to go, may I say?
Sure, sure.
You have to check the product,
Yes.
1, of course, in the select, so where product is like equal 1. normal SQL without a special function, I have to check the date being greater or, well, it's quite difficult. Because we have to check the lower in between the period and the upper in between the period.
It gets simpler. Upper is exclusive upper.
Exclusive, yeah, we take it exclusive.
So lower must be lower or equal than 30, and upper must be greater than the first data.
Yes, exactly. Well, I have my doubt with the greater equal, but it's kind of this query here. So we say the product equals 1, that is clear. And then we say the lower has to be smaller than the end date we ask for, and the upper has to be larger than the start date we ask for.
If the 22 and 30 is inclusive, then lower must be less or equal. It depends. How is the question?
So what I assume here,
must this date be included or not?
it's not included.
Okay, I go.
Okay, okay. Yeah, here I wasn't looking for that particularly. We'll see it on the next slide, but this is basically what we have to do. So it's not so easy basically to find the right predicates. So here let's see. So how to get the prices of product 1 between the start in red and the blue, which is the end. So basically what we have to somehow think of is that the period we are looking for should not start after the end and should not end before the start. Okay. So we basically, now we do it the opposite. We think what we don't want, and then we just negate it. It's sometimes easier to think like this. And then we just have the formula here. So basically, the lower should not be larger equal than the end, and the upper should not be smaller. We can use the Morgan's law, but this is not what I want to show here. And at the end, basically, we get this one here. Okay, so this was exactly the one that we had before. So of course, we don't always want to do such kind of reasonings whenever we want to write a query, or whenever we want to extract some data. So this is actually where range types come into play. They make our life much easier in this regard. So if this is our data, now we go back to the range types. We don't have lower and upper, but we have one data type which encodes it all. And we are asking now for what is the price of product 1 today. And that becomes a very simple query where basically we can use a special predicate of Postgres, which basically has this containment. This is what we are looking. We are looking for the ranges which contain the data. Now to the more famous one, which we looked at before. Okay. So also this one. Postgres provides us with a special predicate, which is basically 2 end symbols. And they say, okay, I want all the periods. The 2 ends indicate overlap, which overlap basically this range that we are looking for. So it makes stuff easier. Okay? So this is the key point of range types. And now, before, when we were looking at this very simple example, we were not even reasoning whether the start is inclusive, the end is exclusive, whether something is infinity. Before I simplified all of this. Okay? But here the range types, they actually take care of that. So it will check the inclusiveness, it will check the infinity and so on. Okay? So this is all handled by the system. And of course, these are just 2 examples, containment and overlap, but we have many more. We have a lot of functions which basically can be used to actually modify and check for these range types. And here, of course, this is a non-exhaustive list. It goes on, but I couldn't keep it on the screen, so I just stopped here. So one thing we weren't looking at is now we were storing prices somehow, but potentially we could have two different prices for the same product at the same day. So this was up to the programmer to basically check that there weren't two prices, that this consistency was basically satisfied. Postgres here also provides us a way to basically have kind of uniqueness constraints over time. So where we can say, okay, we want to make sure whenever we store a price for a product, there shouldn't be another one at the same time. Okay? So this is like the uniqueness constraint in this regard. And this is something we can do. There's a special syntax, which is basically we have the same table as we created before. And we can say exclude, let's skip this for the moment, exclude everything which has the same product and is overlapping on time. Okay? So this means if I try to insert something here with the same product, with an overlapping period, the system will not allow. Okay? So basically what happens is if I sneakily try to increase the price of product 1 today, from 30 to 100, the system will tell me there's a conflicting key violation based on this exclusive constraint. Okay? So again, this is again something which makes our life easier because we would have to check using a query every time whether this constraint is satisfied or not. But again, it would always be left to us. So here it's actually done by the system. One thing I still wanted to just mention in this regard is basically this gist here. So this is kind of a weird syntax to have constraints like this. So we say exclude something using something. So what Postgres did is basically they provide you an index for these range types, and this index is used to check these key constraints so that everything becomes more efficient. But it's basically just an index which is created on product and the period, and this will basically help you for all the predicates we saw before, plus also for this exclusion constraint. Any questions? Yes?
If I need to have if I didn't do the previously this exclude, so in my system there are already products, the one product with within the same period with different prices. How can which one would be the
if I already have it?
If I already have it, and I want to know.
The query will stay the same. It's exactly this query here. It's exactly, so if we want to check basically
Okay,
just for specific one, we use, if I want to check over the entire table, I have to use a join basically. We'll see a little bit on that later, but yeah. Was this somehow?
Yeah.
Okay. Any other?
These are extensions to the standard introduced by Postgres
This is standard data type since 2012. It's a standard data type since 2012. There's no need for an extension, nothing. It's all already there with the standard Postgres distribution.
Yes, it's standard Postgres,
yes.
But it's not the standard ANSI or something like that.
No, exactly. So the standard SQL, so the standard ANSI went a different way. And the way it went actually was by using this one instead of range types. So range types is something very specific to Postgres. Yes. Mm-hmm. Okay. So I think the take-home messages here for the range types is basically this is a native data type to Postgres. It's very convenient. It avoids many mistakes that we do in programming. There are many basically different definitions and data types that we can use with the range types. And the uniqueness constraint is another level which really helps us when we program to basically not make not introduce bugs, basically in consistency. Okay. So this was basically an overview of the range types, which is basically the way how we can manage period data in Postgres. It doesn't go much further than that, so this is basically what we have available. There is one additional, let's say, data type which was introduced, I think, with Postgres 14, with the new version, which is basically arrays of range types. So we can also have that, and we have a lot of functions also for that. But I won't go into detail for that. Okay, so now we move from period temporal data like contracts to time series data, which is basically data where a data entry is associated with a time point rather than a period. Okay, so with Postgres there's one extension, and this extension is called timescale. This is what we can use basically to process time series data. So just a few quick words what timescale is. So timescale is an extension. It does not come with the standard Postgres distribution. You actually have to install it, and it's based completely on UDFs, on user-defined functions. Okay? So there's no change to the system itself. And of course, based on this extension, it runs on server side. It's not a middleware, it really runs on the Postgres server using these user-defined functions. The installation is very easy actually. There are packages already ready for most of the operating systems. In the worst case or in the best case, however you want to take it, you can install it from source. It's very easy. You just take it from the repository, you compile, install it, that's it. And once you have that, you can do everything that we will see now later. Okay, so the key points of timescale is actually that it helps us with some things which are otherwise very difficult. And this is convenient functions specifically for time series data. Okay, so it provides us with that, and that are called hyperfunctions with timescale. It allows us to partition the data for performance reasons, and then we are talking about hypertables. We'll see each of these points later on. And it allows us to do compression of the data, which is a very important topic for time series data. Okay, so let's go into these 3 points. First, just as before, we are looking at one example. So let me directly start with SQL. So we create a table, which is called sensor signal. We have an ID of the sensor. Okay, so we have several sensors. We give it an ID. We have a timestamp. So basically, whenever there's a reading, we will put that timestamp. And the value is simply a float. Okay? So now we have a table where we can basically store time series data. So for the sake of an example here, I generated some data. So without going into detail here, what I did, I generated data for 4 sensors randomly. It's daily data from July 31 to August 4, so basically today. And I delete the data of August 3 so that we also have some missing data. Okay? And this is basically how it looks like. So we have some randomly generated data, and data doesn't mean anything basically. Every day at 6 in the evening, we have a recording for all 4 sensors. And from July 31st to August 4, but excluding August 3. So that data has been removed. This is just how you would do a table. We don't have any time scale here, nothing fancy yet. Okay, so first, when we have such a table, we can already use all the functions provided by timescale without doing anything special here. Okay? So it provides us with a bunch of functions. So you can see arrows here. So it doesn't end up with this 5, but we have a lot of functions. I will show two out of this list, how we can use it. We have, for example, interpolation functions, gap filling functions, which is very important in time series. We have weighted average, downsampling, upsampling functions that we can have. Statistical aggregates, so to calculate kurtosis, skewness, and all these kind of functions. Okay, so I'll of course not go through all the list, I'll just show two and how they work. So let's assume we have our data of before, and instead of having a value every day, we just want a value every 2 days. Okay? So basically we want to reduce the granularity of the data. Remember, timescale is based on user-defined functions, which means we always call a function. So if we want to produce a value for our sensors every 2 days, okay, here I don't even include the ID, I just make over all the sensors, we can use the function which is called time bucket. Okay, so this is a function not standard Postgres, this is timescale. We can say a granularity. Okay, so in this case, we want something every 2 days. We can specify 1 day, then we would get the value every day, and so on. We can specify hour, we would get the value every hour. We specify the attribute where our timestamp is in. The aggregation function we want to create over the data for these specific buckets. One particular sensor that I extract here, and I order it by the days. Okay. So basically what we get is, if we go back to our data, this was our starting data. What we get is basically buckets for sensor number 3. We get buckets of 2 days length. And the value that we get is basically the average, which is the average of all the sensor readings in these 2 days. We can use maximum, we can use minimum, we can use any kind of aggregation function that we have. Okay, so this is basically time bucket. So if I specify now here 1 day instead of 2 days, okay, I will get a sensor reading every day, but not for August 3, because it doesn't have any data on August 3. If we additionally want data on August 3, so if we want to do gap filling, there is a different function which is called time bucket gap fill, and in this case it will actually fill the gap. It will basically make sure that from August 31st till the July 31st to August 4th, we have a value every day. Okay? If I produce the standard average, this value will be empty because there is no data that we can produce an average on. But timescale provides us with a function which is called interpolate, which basically does linear interpolation for the days which are missing. Okay. And we basically call it exactly the same as the function before. There are just two kind of things that we have to be careful here. One is interpolate is linear interpolation, which means if we don't have any value before, we cannot do linear interpolation. Right? So if our first day is missing, we won't get anything here. Okay? So if we have no value on July 31st, then basically also this one. And the second, which is maybe a bit a limiting factor, is that this here is mandatory. Okay. So we have to specify, we want the data from this time point to this time point. And the reason for this is that this instructs the function to know where to start and where to end. Okay. If we don't specify this, it would kind of like being, we want from -infinity to +infinity. Just give us all the dates. Okay. So in this case, the system basically looks at this query. So the extension looks at this query. It will figure out in the where clause the start and the end. And then it will basically start from that specified timestamp. So I have to hard code basically this in my query. If I don't do that, if I drop the between end, the system will give me an error saying that it can't infer where to start. Okay. Any questions? Okay. So this was basically the function. So there are many more, but this is like a catalog of functions. So I just showed two here. But they are all called basically the same way. These are just functions that we can use in our queries. Another help that basically timescale gives us is the hyper table. So it allows us to do partitioning of the data. So partitioning of the data, if you have a large data set, you want to do partitioning so that basically your queries run faster. And what timescale does is basically we use the same table as we created before, and timescale will partition it into a specific way. Okay? So here you see that basically these small boxes are within the large box. So the large box is what we see, one big table. And timescale has the capability to basically partition it along one dimension along time, and the other dimension along something that we specify the system. It might be the different sensors should be partitioned rather than keeping them all in the same table. Okay, so we create the table just as we had before. And this is basically the table that we work with. So now what we do is basically we call a function, and this function will create from our original table, it will create a hypertable, a table which is partitioned. And we again call a function, so it's all about functions here. We say create a hypertable. We specify the name of the table, which attribute is the timestamp of our time series. Then we specify the partitioning along time. Okay, so we say create a new partition every 2 days. And additionally, we can have an additional column to partition. So time is only one dimension, but we can also say partition along the other dimension. We give the attribute. So in this case, we also partition by different sensors. So different sensors might be in different partitions. And we specify a number of partitions for this additional attribute here. Okay? So here, what we basically get is we store data. Every 2 days, it will make new partitions. And it will, for all our sensors, it will basically partition them into 2 different ones. Okay? We'll see an example later. Basically. Okay. So now I have to check how to do that. Okay. So now, wait, okay. So this is basically just here I connect to Postgres, just the terminal. And what I additionally have here is basically I have this timescale DB extension loaded into the system.
I don't hear.
Sorry. We have this timescale DB extension loaded into the system. Okay, so get out. So basically here I just used the source code of timescale.db. I compiled it and loaded it to the system, but again there are many different, let's say, ways to install it. Okay, so now okay. So now I prepared the script. So basically we will create the same table. Yeah, I show you my. I'm sorry for that. We basically create the same table as we had on the slides. So I'm pretty sure I have the table already, so I drop it. So I dropped the table, I created a new one, traditional Postgres table. I insert the data that we had on the slides, and that's it. So this is the data that we have. Okay. We have 4 sensors. we have no data for August 3, and that's it. It's randomly generated data. Okay, so now one thing we can look at is basically this hyperfunction. So this was the hyperfunction that we had on the slides. Okay, so we have this time bucket, which will basically use only the data of sensor 3 and create a value, which is basically the average, every 2 days. Okay. I can specify every day, just to change this one here. Okay. Now it's still called 2 days, but this is now data every day, and you can actually see that August 3 is missing. Okay. So for performance reason, these are basically two functions, one which does gap filling, one which doesn't. Now let's look at that one. So we look at the function which basically does the gap filling as well. Okay. So here we basically use this time bucket gap fill, 1 day. We have the average. You see that the average is basically, there's no data, so it will basically tell us there's nothing. And the interpolation, we basically interpolate the average between the day before and the day after. We'll just do linear interpolation. Just to change a bit, we can maybe put here 12 hours. So this will basically give us a value every 12 hours. And you see there is basically the interpolation going on because we don't have a value every 12 hours. Okay, and now I just show you if I remove this one here. It will basically, sorry. So now I'm basically asking for gap fill without specifying the start and end.
You should delete end, I think.
Yes, fair enough. Thanks. So basically it tells us it cannot infer the start where to do basically the gap filling in the data. Okay. So this is basically an error that we get from timescale DB. It tries to look at the where clause, start and end, and then try to create basically that. Okay, so now we basically had our traditional table. So let's again look at our data. Is it large enough? You can see it, right? Okay. This is our data. And now just let's also look at this query plan so that we are really sure that there's nothing weird. So this is basically the query plan of the query. It basically does look at the table, sensor signal, scans the table, and gives us the result. Okay, so we know there's only one table here. Okay, so now we basically, out of this table with the data, we create a hyper table, which is then partitioned. And this is exactly the same as we had on the slide. Okay, so basically now we created partitions for this. So let's rerun this query here. It looks exactly the same as before. Okay, so we of course have the same data, I hope at least, yeah. But if we now look at the query plan, that one will change. Because now we don't have one table anymore, but we have all partitions. So basically now we see a timescale created 1, 2, 3, 4, 5, 6 partitions. So partition every 2 days, and for every 2 days, and for every 2 days we have 2 partitions. Okay, for the idea of the sensor. And these are basically the one that we see here. They are called chunks, but they are nothing. They are just regular tables. And of course, now if I want to read the entire data, then somehow timescale or Postgres has to look at all of them. Okay, so this is the idea. But the idea behind is basically that whenever I look for something specific in the data, I don't scan all the data, I only have to look at a few of these chunks, not of all of them. So, for example, if we basically now look only at the data for sensor 2, we specified 2 partitions for the sensor ID, which means instead of scanning the 6, it will only scan 3, I hope. It will only scan 3 tables, because the data of sensor ID 2, is only in 1 table. And every 2 days we have 2 tables. But it knows that the sensor ID 2 will only be in 1 table. Okay? So this means now we basically removed half of the search space. Okay? So we don't have to look at all the data, we only look at half of it. We can do the same for the time. Okay? So now we are looking at all the time series between the 3rd of August and the 4th of August. Okay. And it has to scan 4 out of 6. Okay. Now, if we combine the 2 things, we are looking for one specific sensor and even a time range. Okay. It only had to look at 2. Okay, so out of 6, it only has to scan through 2 relations instead of all 6. And this is basically done by the partitioning scheme, which is given by Postgres. Timescale only helps us with creating the partitions, but the partitioning itself is based on Postgres. Okay. So you can create your own partition in standard Postgres, just you have to do it by hand. Every table has to be created by hand. Timescale does it automatically for you. Okay. As long as you store time series data, of course. Okay, so let's see. Yes. Okay. Okay. So this is a very nice thing. There's just one drawback. We don't have a lot of control over the partitions. Okay? So you saw we created 6. If we insert data, more data, it will create more and more and more and more. Okay? So basically, we have to be really careful with the partitioning. Whenever you fetch data, it will basically have to go through all the partitions. It has to look through all the partitions. So new data keeps on adding. So just an example. If we store data of 100 sensors, 3 years of data, and by accident we specify create new partitions every week, and make 50 partitions for the sensor IDs, we'll end up with 7,800 tables. So if I scan all the data, Postgres will have to go to 7,800 tables. Okay. So we can try it. It doesn't take that long. So, I will drop our old table and now create a new one with 200 sensors, data from 2022 to 2025 on a daily basis. Okay. So this is now basically, this is just the regular Postgres table. So we can have a look. Okay. So this tells us basically, okay, there's one table, it did a parallel sequential scan of that table, that doesn't really matter. It scanned one table, we just created one. The planning time was half a millisecond, and the execution time was 25 milliseconds, okay, to fetch the data. Now let's create a hyper table out of it. So we create new partitions every 7 days, and every 7 days we create 50 partitions. Okay, that's it. So now let's basically, before what we got was this. Scanned one table, planning time half a millisecond, execution time 25 milliseconds. Now let's run the same query again. Okay, so it's actually pretty fast, but now you can look at the query plan. These are all the tables it has to scan. It's around 6,000 something. So before I told you it was 7,800, I didn't really lie. This is the maximum it will create. Okay? The partitioning along IDs is by hash, and it doesn't have to be that out of 100 sensors and 50 hash partitions that every partition is filled. Okay? So we have slightly less.
As you go into the future, I mean 2025 in the future, so by definition, most of the things are empty, right? Because you don't have data.
I actually insert data.
Oh, so you simulate, okay.
Exactly.
Because I was just
No,
thinking
sure,
about
sure.
it.
Yeah.
Sorry.
Afterwards, it will be empty. So
Yeah,
it
great.
will only create tables if I insert data. Okay. So if basically we count the number of chunks, the timescale created, we basically, it's almost 7,800, it's 7,741. Okay, it's slightly less because not every bucket is filled. Okay. Oh, okay, so this is basically something we have to be careful of. Even worse, when I created it the first time, I wasn't even able to delete them anymore because it needs 7,800 logs. And by default, we don't have that. So you actually have to increase even some parameters of Postgres just to be able to delete it. Okay, so basically just be careful how you partition. Think in advance, what is the time frame, what is the number of partitions. And remember, this is basically a multiplier. Every 7 days, we'll define a long time. Okay? So if we have 52 weeks a year, and we store data of 3 years, we have roughly 150 times the partitions we create every 7 days. Okay? So remember that this basically multiplies. Okay, so this is the hyper tables. So let's look at the compression. So this is, now we had the partitioning, we had the function, we had the partitioning, and now the compression. So the compression is basically something to reduce the size of the data, but also to improve performance. So when we actually used timescale DB, we saw that this actually substantially improves the performance. Smaller data, less to read, basically. So in timescale, you have to enable compression on a hypertable. Okay? So you just alter the table and set 2 parameters. And then what you have to do is to basically compress every chunk on its own. For this, it gives you a little bit of help. So you can say, okay, I want to compress all chunks which are older than 1 day. Okay, so which lay 1 day in the past. And you can actually do it with this query. It gets the chunks. It basically looks if they are older than 1 day and then just compresses them. Now I just want to show you how it works. Okay, so for you it's basically completely transparent. You don't even see anything about this partitioning, but still it's important to know how it works. So uncompressed, data looks like this. Okay, so this is one of these chunks that we created before. This is one table. It includes 3 sensors, and it includes data of 2 days, the 2nd of August and the 3rd of August. So one tuple without data in Postgres costs 24 bytes. Okay? So if we calculate here how much this needs storage, is basically we have 6 rows. The tuple header is 24. The first is an integer, 4 bytes. The second is a timestamp, 8 bytes. The last one is a float, 4 bytes. We calculated 240 bytes. Okay? You see the dominating thing actually comes from the 24. The header alone is larger than our data in every row. So what timescale does is basically it compresses the data, it transforms the tuples into arrays, okay? Without even you noticing or without you seeing it. So now if we calculate again, so we have exactly the same data as we had before, just now this 2, 2, 3, 3, 4, 4 is stored in an array. Okay? Same for the timestamp, the same for the value. So now if we calculate again, we only have one row, which makes tuple header only once, and 6 times just the data that we actually store. I put this epsilon because the arrays cost a little bit, but it's 120 bytes. So we basically reduced it from 240 to 120. We halved it, only for 6 rows. The more you have, the more basically you save. So this is basically one type of compression. The other type of compression is basically by keeping one attribute out of it. Okay? So for example, the sensor ID. And this is called basically a segment. So we don't store ID 2 twice anymore in an array, but we have more rows. Okay? So it's kind of a trade-off. So if we calculate it for these 6 rows, we end up 164 bytes, which is a little bit worse than before. But once, let's say, the duplicates that we have here pay off this 24, we actually would be better off than with the solution before. Okay, so now I try to go back.
So this chunk is one of the tables in which you partition.
Exactly, it's
the
one
original
table.
one.
Yes. So the compression happens at per chunk level.
Okay.
So now, I should better not do it. We still have these 7,800 rows, tables. So it takes a while to delete. Yes. Yeah. And now we have the same data as we had before, not the 7,800 tables. So now I basically go down to compression. So we compress it with the variant that we had on the third slide. So the ID stays out. I have to make a hypertable. So this, of course, only works on hypertables. Okay. Now I enabled partitioning, compression, but I didn't compress anything yet. So now I compress basically all chunks which are older than 1 day. Okay? So it basically compressed 2 chunks. And it's basically these 2 here. So this is a regular table. This has now been transferred into an array. If we look at it, for us it's still a table. There's no array going on. So this, everything happens in the background for us. But we can actually see one difference. So what happened is basically, if now, this is one of these chunks which has been compressed. Okay? So something has to happen in the background without us knowing it. Because these are now arrays, this is not tuples anymore. And we can actually see if we look at the query plan, so we can actually see that there is a decompression going on here. Okay? So the scan happens on the chunk that I just asked for, which is the compressed chunk. And timescale does a scan on actually a completely different one. Okay. So the original chunk is just there for Postgres so that it has the same schema, there is no array. And timescale, whenever you try to read that table, it actually redirects you to another one with the array, and it will decompress them on the fly. Okay? So basically now, if we try to read our entire table, and look at the query plan, we actually see that there is a regular scan going on for non-compressed chunks, but for compressed chunks, there is something in the background which has to happen. This, of course, costs a little bit, okay? But it usually pays off because you have much less data to scan. Yes, and there's one more thing I can show you just quickly. So if we look at the table size of a compressed chunk, so this is just some way how I can get the table size from Postgres. Now let's check one which is not compressed, which is this one. Okay, so one which is not compressed, which is this. So at least one parenthesis. Okay, so it's 800 bytes. It includes some headers, so don't really worry about that. And now, this was a non-compressed one. Now, let's check the size of a compressed one. Zero. This is because this table is only there so that Postgres has the same schema. It has a table which has the same schema. But timescale actually stores the data in a different table, because you cannot have a partition table which has a different schema than the original table. Okay? So here Postgres timescale basically does some moving around, but you basically don't notice. If you read the data from this table, it will redirect you to the other one. Okay? So you can do the traditional query as before. Okay.
In terms of performance, how much do you lose?
You actually gain because there's less data to scan.
So,
So in most of the cases, you lose substantially.
okay.
You gain substantially, sorry. Yes.
So you gain memory and you gain performance.
Exactly.
Win-win.
Yes. Which generally for data is always like that because the compression itself, so this is all CPU, this is not really expensive. What is really expensive is basically reading the data, transferring the data. This is expensive. So that's why in this case, in most of the cases, in such kind of applications, if you compress data, you actually gain performance.
Question.
Yeah.
You created these compressed tables with a special select statement.
Right.
There was a where clause where data some sort of period interval older than
Yes,
1 day.
exactly. Mm-hmm.
Is this a metadata change? The question is the time goes on.
No, you have to do it by hand every time.
Okay. This is
So-
statically created.
It's always, everything we saw is static, you have to do it. So if tomorrow you want again all the data to be compressed, you have to do it.
So you have to some job.
Exactly, yes. Yeah, that you have to do.
You have to use a scheduler.
Exactly.
Runs the compression every day.
Exactly.
Are these data modifiable? Can I insert some data into these compressed tables?
With the newest version, it works. With the oldest, it not. So this is still a system which is under development. And now with the new version, you can actually. What they say is that you should do it on the read-only data because it costs a little bit more to actually insert data. Because when you insert data, you just insert it in a table. But if you have an array now, you have to basically delete that row, make a new array, and insert the array again. Okay? So it costs a little bit more to insert. So that's why it's better to do it on some older ones.
So for example, it would be a good way to be used for IoT data coming from sensors because they won't probably change for the past.
Yes, and if you know that your data usually arrives 1 day in delay or 3 hours in delay, you can actually use that for this.
And you use the time
exactly.
older than and greater than your time period.
Yes, but you have to do it by hand.
Yeah.
So. Okay. I guess I ran out of time, so take-home messages here is basically timescale tries to handle time series data transparently. You have a table. You only have a table. You can use all the SQL. You can use everything plus all the functions they provide. It's just everything in the background changes, but for you, nothing when you build. These hyperfunctions are very handy actually. They are most of the time they are much faster than what, now I don't want to say you, but what I would create as a query. Okay? So they are faster than writing your own query from scratch. The hypertables are very useful. They limit the search space when you scan data because there are some data parts which are not even considered, but we have to be careful with the partition. So we don't have to create too many partitions. There is no good number, of course. So as it usually happens, here there is a trade-off with the partition. At the compression, so from our experiments, it always improves performance, except if you have to insert compressed, basically, data. Okay, so I'll probably skip this one because we are late and just say thank you.
So, I don't know, we have time till 8 o'clock or 8:30 also for the discussion, so if they want to see the last slides and they are agree, we can even
So
extend the
last slide
takeover.
is just
Up to you guys, if you want to stay or not.
It's 3 slides, which basically says what we are doing until the event.
Yeah. This was exactly my question, because I know you also did some work on some extension, so that would be...
Okay. Okay.
Show us what you as fully presented.
Okay, fair enough. Okay, so basically in this regard, we are working on 2 projects. One is called iStep and the other one is called Premise. This was basically the funding I had at the beginning of the slides. And one project is basically about this period temporal data and the other one is about the time series data. And what we did basically in one project is we were working on joins which involve overlap, and the key idea there is basically to improve performance. We'll see 2 slides later on. Other things we were working was basically queries. How can we best write queries so that we can find anomalies in the data? So if we have temporal data, we want to find anomalies. So for example, overlapping prices which basically decreased one after the other. And here we are focusing on the healthcare domain. We are working on basically key foreign key constraints and histograms for cardinality estimation. So this is all with being data. I will pick out one for an example later on. In terms of time series data, we basically have a project with 2 local companies, which is about the predictive maintenance of industrial equipment. And this was basically where timescale came in, where we basically experienced and we looked into timescale. And this was basically the place where we had to develop this data ingestion infrastructure and the data storage infrastructure, and we also had to extract interesting insights from the data. So that's what we used, basically timescale. Now we are basically working on trying to contribute to timescale as well, because it's an extension, it's a very nice project, and it's definitely worth working on that. So for the first, I just pick out one example, one simple example that we worked on, which is basically, if you remember this overlap query that we had at the beginning, we can also use that in a join. Okay? So here we have an example. So we want basically, we have a table employees that stores contracts of employees, and we have a table projects, and we want basically all employees which overlap with the project duration, so that we can actually find the employees that we can assign to this project. Okay? So that's why the contract of the employee has to overlap with the period of the project. Okay, so this is basically, if we look at this query, so Postgres does provide an index to do something like this with the range types, but it's not a very efficient index. Okay? So the most efficient index is actually this B3 index, that when you create an index in Postgres, this is the default. This is the most optimized index. Okay? And also other join algorithms, they are not good for that. I mean, hashing, merge join, this simply doesn't work with this kind of smaller, larger. So what we did here is basically we figured out a way how we can have this query and transform it into a different one, which is 100% equivalent. Okay? So instead of checking that, we check in one case that the start point of one period lays within the other period, and independently that the other period start lays in the other period. Okay? So instead of checking overlap, we check containment. This is the key point of these 2 queries. And that,
is there an error?
no, this is actually,
Is there the P not upper? Well, lower E,
yes,
not lower, less than P upper.
exactly. So basically,
Is this not an error?
I don't see where. So if I can see,
I
I can explain it.
The well clause does not give us all employees which are valid on the period of the project. Lower.
Yes, exactly. So I can quickly explain.
Okay.
So here we are checking overlap in one shot. In this query here, just look at the first one. This means basically that the start point of the project has to lay in the entire range of the employee.
Must be fully available.
Exactly, within.
Okay.
Mhm.
This is another.
This is one query. And the query below basically checks that the employee's start point lays within the range of the project.
Mhm.
Okay. So we can prove that this is exactly the same as this. And here, the nice thing, we don't have duplicates. We have a union all. So this means we can run these 2 queries independently. So just by using this now, we can actually use B trees, which are the most efficient.
Mm-hmm.
And basically then our query plan looks like this. Okay, so we have these 2 queries, and each of them can be answered with an index. Okay. We did one more work here. So basically, instead of using an index, we developed a join algorithm which does it. Okay. And this was basically developed by a student. So basically, instead of a merge join, we implemented a range merge join in Postgres. And this can actually handle these containment predicates. Okay? So if you run a containment predicate, there's a new join algorithm which basically runs this stuff independently. Okay? And here we can actually gain, for joins, we can be 10 times. So with this approach, we can be 10 times faster than the index that is already in Postgres. And with this one, you can add another 10 times. Okay. So this is basically what we worked on. And of course, here the source code of this one is available. Okay, so this was just a quick example of what we did. Yeah.
So, thank you, Anton, for the nice presentation. Now it's your turn for questions.
This is my email, so just drop me an email if you have questions.
Could you say a couple of words about the licenses of timescale?
The license? Oh, I have to check. But it's actually, I think it's Apache license. So
Not
so
anymore.
There was some.
It changed. It was Apache, but it's not open source anymore. You can still use it gratis, but it's not open source. It's the timescale license, yeah. They did the same thing as MongoDB and Elasticsearch and all these guys.
that's okay.
So that's indeed a little bit
Yes.
bad, but
Okay, that's fine. Since which version?
I don't remember. If you go to their site, they show the difference. Just open their site.
Yeah, this is the one that I have here.
The older one is the Apache, and newer one is a thing called the timescale DB license.
But this is the newest, actually. This is the source code newest.
What did it say? I did not
There
see
was
it.
Apache.
timescale license.
No, but go to their site, because there's also, at
The
some
second
point, there's
one.
also a matrix where they explain the difference in features, etc.
So I just use
Maybe
the
you
source
have
code.
the last Apache or the latest Apache.
Exactly, but because I always use the community version. Which is
Okay,
basically
yeah,
from the-
maybe
Yes.
that's the difference. Then.
Yeah, I compiled it. I compiled it
But
basically from source.
anyway, if somebody's interested, just go to their website.
Yeah,
They explain
okay.
it very well.
I will also check it out. But probably the source code, the community version is always with Apache.
I don't quite remember how they call things.
Yeah, okay, fair enough.
If you want some set of features, I think I just did a presentation on this thing, but I also don't remember quite well. I think if you compare, the community version does not have some of those hyperfunctions.
That might well be,
If somebody's interested, I
This was-
suggest just to go to their site, not to the GitHub, but really to their homepage, to timescale DB.
But everything we basically used for the project, plus
This,
everything I showed here is basically based on
Yeah.
this version here. Yes. Yeah, that might well be.
Yeah, it is the usual mess because they were afraid that the big guys would just because they're offering a timescale as a service.
Yes, exactly.
They don't want the big guys to offer it as a service. It's the same story
Yeah.
as MongoDB.
Yeah, that is annoying, yeah. But again, we use this version, and let's say all the functions we had before were available. So, yeah. And many features are so all the partitioning is Postgres feature.
Yeah, exactly.
So-
Yeah. If somebody is interested on 2006 org, my website, if you go to the blog somewhere hidden there is also a presentation about that.
Cool. I'll check it out.
It's basically the same thing you did, but worse. So Anton's is basically better.
Not sure about that.
But the main message is indeed that most of these features are just native Postgres. It's just that the
Exactly.
timescale offers you some comfort. For example, you can do everything with partitioning you can do by hand, but of course timescale does it automatically.
You can also do the compression by hand.
You could also do
You
the
can create an
arrays
array.
by hand. Yeah, you can do
It's one query, basically.
except for those hyperfunctions that you can't do. Well, you would have to code.
Yes. So, some of them we already had it before, so some of them can be emulated with window functions. But the query, of course, you have to write the query, that is annoying. Yeah.
You probably you should really check out what you need, because if you read their manual, they sell everything as if it you need a timescale DB to do it.
No, you
because
don't.
they of course they want to sell a timescale DB, but then again you really should look for yourself if you.
Sure. I mean, most of the things you can do it already in Postgres. Just more convenient.
It's pretty cool. I sort of like it, but probably it's not for everybody. I mean, it's probably. I see. I also work in this space, so often people think, oh, I have a problem, something is slow. Okay, I just inscript timestamp DB and everything will be fine. Often this is not the case because the problem is somewhere else, maybe in the client library or.
I remember the first time we actually imported data, it was actually slower. And this was because we overdid it with the partitions.
Yeah.
So I think I remember we had 50,000 partitions. And if, let's say, a select account star on the original table would cost you like 10 seconds, in this case it cost you like a few minutes.
Yeah, that is.
So you can also overdo it.
Yeah, sure. But that is also the native Postgres.
Yeah, exactly. Partitioning is native. Just
You
you
should
have to
probably look in also what is your use case. One very good point about partitioning is I can speak loud and probably everybody will hear me. One really cool thing about partitioning is if you rotate stuff. So you say you have a retention and then delete the old table. With partitions, it's much more efficient because you can just drop the old partition. Because if you do a delete, then you end up with unreclaimed space. Yeah, you have this vacuum problem in Postgres. And by dropping the partition, everything goes away cleanly. For example, this is something very handy. But again, you should see if it's worth the effort to read the documentation of timescale DB, etc., etc. If you just need one single feature, maybe you're quicker just doing it with native Postgres. But it's quite cool. I also like it.
Yeah, that is a good point, of course. If you just need partitioning, you can do it with Postgres alone.
A question to the organization. Will the presentations be online somewhere? Or?
If it's fine for Anton, I can share it per email with all the participants.
I can also put the script if you want.
Is it on YouTube?
Yeah.
Okay. Yeah, then,
Okay.
Just
But
share the link.
If you want the presentation, then.
Where did you hide the YouTube camera, Stefano?
It's there.
There. I see. No, okay.
One more question. If you're using timescale DB, do you have take any particular precaution when you're doing backups and if you're doing updates of timescale DB? So for Postgres, you had to run a special query to update all the function definitions. Is there something similar for timescale?
I actually don't know. So, in principle, so what is in the tables is basically Postgres. So as long as they support the same, it should go without problems. But of course, if they change their own schema and as it was for Postgres, then they will probably have an update script. But maybe Chris knows more.
So I don't use it in production, so I never updated it as well. I would also not know.
Yeah, that's good point. Yeah.
Someone else has comments, questions?
I recently read a blog article about what was it? MariaDB. Time series data, time series tables, and this is an SQL standard. The question is if Postgres supports this standard. There is a special select syntax and update syntax too. It can create records if you have a record with a certain validity, and you can update this, and the statement automatically splits this record. It makes 3, and the question is Postgres supports this standard too.
So this is not the time series, this is the period data.
The period.
Exactly, yes. So this is basically an SQL standard since 2011.
12.
12, I think the standard is 11, but Postgres does not support it.
Okay.
So I think it's Oracle, Microsoft SQL Server, a bit MariaDB now new, but only a portion.
Mm-hmm.
So this was a standard which was a bit, not fully covered by the systems. You can emulate it somehow in Postgres, but the standard is not there now.
How about unique constraints? If you have a table with a unique key and you transform it in a period validity, in Postgres you have to use this special exclude syntax combined with the keys which must be unique.
Exactly, yes.
Because we have seen an example which regarded only the period. But sometimes we have a code which must be unique, and these columns have to be combined with a period.
Exactly. So here I have to say 2 things. So this is basically the combination of product, which would be your code, that has to be checked with equality, and the period with overlap. One thing I forgot to mention here you have to load an extension in order to do that, because there is a B2 gist which supports equality plus overlap, so it's not by default. By default, you can only do overlap. If you have this additional extension, they actually write it on their documentation, you can actually do both. And this is actually also a project we are working on. So to make using B trees based on our rewriting to have these key constraints, but also foreign key constraints. So we actually already have it. We'll put up the code in a few weeks, I guess. So there, it's basically based on just Postgres functions. You can say, make this a key with this period, and the foreign key with period, and then it will basically enforce it afterwards.
I'm just short-sighted. No, I just can't see. I did not know this syntax. With equal, it's a strange syntax, isn't it? What are with equals?
This one?
Comma? Yeah.
Yes, so basically exclude using the index, product with predicate equals, and period with predicate overlap.
Okay.
So whenever it's the product is equal and the period overlaps, exclude it.
Yeah, it's a cool syntax. I didn't know it. It's cool.
Yeah. So the SQL standard in this regard actually doesn't have this range type, so it has a start and an end as a regular data type, and you can declare it as a period. So they did that in order to not have it change they didn't introduce a new data type. They just said now you can declare it as a period so that JDBC and everything stays standard as before. And in the standard, you can actually say primary key, as you would do for a traditional primary key, and then you specify the period keyword and the period, basically, that you declared in the table.
Combined with other columns.
Exactly, yes.
So, if I understand right, this index make a condition about the operator which is used when I invoke.
Yeah, kind of. Yeah. So the reason is it would be able, of course, to do it without the index. It just would need to scan always the entire table. if you create a primary key on a table, it will create a B plus to the index. There's no primary key without an index. And here it does it with this GIS. So this is this general inverted search tree, which basically can handle this break. It's kind of an R tree on basically. Yeah, it's a bit, we were working actually on some features of the standard, but yeah, I mean, Postgres has range types, so they are cool as well. I mean, they are very cool actually. There are a lot of predicates, functions, quite convenient, but this automatic update, delete policy is not there.
We work with multiple databases, so I could never support only a special database like timescale. It is a no-go.
Okay.
Someone over there wants to say something, ask something.
Well, again,